So we've been talking about thermodynamics here, and last time we got into Gibbs free energy, and a reminder that there's a few different ways that we could calculate Gibbs free energy. It is basically the energy available to do some type of work. There is an equation where if you do have the delta H and the delta S sort of given to you, you can obviously use this equation here. Delta G is equal to delta H minus T delta S. We also can do our delta G is our delta G of our products minus the delta G of our reactants, and just look up the values as we go through it. So we can use delta G to determine if a reaction is spontaneous. If delta G is negative, the reaction will be spontaneous. The way it's written, if the delta G is positive, it will be non-spontaneous the way it is written. So I think that is where we sort of left off. Any questions on that there? Okay. So we could actually use this equation here to help us calculate or sort of figure out whether or not a reaction will be spontaneous or non-spontaneous based on sort of the sign that we see for G and S, or H and S. If we have delta H that is a endothermic reaction, it would be a positive number. Our delta S, if it was increasing in entropy, would also be a positive number. So in that situation, you also have to remember that we talked about in terms of units. This guy is kilojoules, this guy is joules, and there is about a 1,000-fold factor there difference between them. So in order for this guy to really sort of overtake the first number, we do need it to be really, really high temperatures. So if it is really high temperatures, then that will turn our delta G into a negative number, and it will be a spontaneous reaction. If we have a positive delta H and a negative delta S, that negative and negative will turn this whole thing into a positive number no matter what the situation is. And we will end up having a non-spontaneous reaction at all temperatures, because we will end up always with a delta G that is positive. Other couple of combinations that we could have, obviously, here is if we have some negative delta H. So if this guy is negative and this guy is positive, in this situation, no matter what the situation will be, what the temperature will be, we will always end up with a negative delta G, because temperature will be positive, S will be positive, and we got the subtraction here. So this reaction will be spontaneous at all temperatures, regardless if you have a negative and a positive. Last combination would be a negative H and a negative S. That negative, once again, is going to turn the back part of it here positive. So at low temperatures, we will still end up with a negative number. At higher temperatures, we could potentially get this part of the equation to be larger and turn it into a positive number. So a lot of times you may be asked, using this equation here, to, you know, if H is positive, S is negative, or something like that, you can predict, you know, based on the temperature, if you would think it would be a spontaneous reaction or not, based on the sign of delta G that you should get. A lot of questions in thermodynamics, you know, sometimes will not give you numbers. They'll just kind of give you things like that, like this is positive, this is negative. You know, do you expect it to be the reaction to be spontaneous or non-spontaneous? Sorry, I got exothermic and endothermic in my head. Any questions on that? So a lot of times you can kind of just look at the equation and the value is given to you to make that determination. So let's talk a little bit about that. So let's say we have this reaction here of calcium carbonate breaking down into calcium oxide and CO2. And let's say the delta H for this guy is 177.8 and the delta S is 160.5. Let's say at 25 degrees Celsius, is this reaction going to be spontaneous? So I want you to take a second or two and do that calculation. be multiple ways to sort of calculate delta G. We've seen 2 so far. Again, you really want to sort of choose the way that, based on the information given to you. So in this case, we are given the H and the S, so it would make sense to use the delta G is equal to our delta H minus T delta S. We do need to turn our temperature, obviously, into Kelvin here, and we're going to add a 273, so that should be a 298. That would give us a delta G that's equal to, in this particular case, 177.8. I personally here am going to multiply by 1,000, and the reason I'm going to multiply by 1,000 is so that my units will be the same. That's going to turn it into joules. We're going to minus my temperature that's been converted into Kelvin and times it by my delta S, which is in joules, which is, again, why I personally here took this guy to joules. You obviously could take the other guy to kilojoules, but you do need to do a conversion on one of them so that they are in the same unit, so you're not off by a factor of 1,000. We do a 177.8 times 1,000 there, minus a 298 times a 160.5. Looks like a 129,971 joules, or roughly about 130 kilojoules here. First off, any questions on the calculation? Is this reaction spontaneous here at 25 degrees Celsius? It is non-spontaneous. Again, here we have a delta G that is positive. So we know that this reaction is going to be non-spontaneous. And we do see that here on the graph. It's pretty much flatlined here at the temperature, or 25 is somewhere in that arrow, I suppose. So could we figure out at what temperature this reaction would become spontaneous? And the answer is, yeah, we can. We could actually use the same equation here to help us sort of figure out at what temperature would perhaps this reaction basically become spontaneous. And we could do that by basically setting delta G equal to 0, because we know delta G basically needs to become negative. So kind of to the left there, 0 is negative. So if we set delta G equal to 0, that gives us 0 is equal to our delta H minus T delta S. Rearranging, bringing the T delta S to the other side gets us a T that is equal to the delta H divided by the delta S in this particular case. So once again here, I'm going to put in our numbers, which we do have these numbers. So I'm going to take my 177.8, and once again, I am personally going to multiply it by 1,000. That way I have joules on top and joules on the bottom, so everything cancels out correctly. You do not want to leave them in the different units. And if I do all that good stuff there, 170, that is not it, 177.8 times 1,000. A little dividing, a little equals. We'll call it about 1,108 Kelvin would be the temperature at which this reaction would become spontaneous. And for reference sake there, if we subtracted 273 from it, that would give us roughly 835 degrees Celsius. And I see that number on my graph, which is a really good number, I suppose, that they match. So that number that we just calculated would technically be the minimum temperature that you need to reach to turn this equation or this reaction into a spontaneous reaction and for it to basically occur. And we do see that at the graph. We're pretty much, by the way, we're looking at the pressure of CO2 versus the temperature. And if you look at this equation, it is only CO2. It's the only gas there. So the only source of pressure would be the production of CO2, which means if we don't produce CO2, we are flatline like we were here. So it's not really until we get to 835 degrees Celsius that we really reach 1 atmosphere, which is sort of standard pressure. And this reaction should be spontaneous at that point. Do we get a little bit of pressure before that and a little bit of making? We do, but technically this is sort of where it would reach sort of 1 atmosphere of pressure, and that would be what we would consider sort of the minimum temperature for this reaction to sort of become spontaneous. Yes. Yeah, it would probably it would still work out. You would still work it out the same if that's sort of your question. If you had multiple gases, because probably the delta H's and the delta S's would take into account the multiple gases that are there on the product side. So those values would come from obviously using those values for those gases. So you would see the kind of a similar. You do a similar calculation if you had multiple gases. In this case, for sure, we know we're really not seeing any products being formed because we do have just one gas, and that would be the only thing that would cause pressure. So that's why we can know for sure we're not really doing much here where it's all flat line all the way through there. And until we start seeing it rise, there's that production of that. You may actually see it maybe come up a little bit earlier in this sense. This may start rising maybe a little bit earlier since there's some maybe multiple gases in that situation, but it probably should still come about whatever you calculated as sort of the minimum temperature is where you should start to see that rise occur. Other questions? Yeah. So technically speaking, you are free to choose if it doesn't specify. Just a rundown of units like we talked about. Typically speaking, common units of delta H and delta G, they're usually reported in kilojoules. So that's very common, the units that we use for those guys. It is delta S that is commonly reported as joules. But technically speaking, if they really don't specify, you could give it any unit of energy that you want. But these are the kind of the common units that you usually would report for these guys. Other questions on that? Now, based on what we were talking about at the beginning here, we could have perhaps predicted some of this. In this case, we had a positive delta H, and we had a positive delta S, which once again, because the delta S is in joules and this guy's in kilojoules, it is way behind in terms of magnitude. So we would need a very high temperature to get this negative term to be a larger number, right? And turn our delta G into a negative number. And I would say 835 would account for a very high temperature to do that. But as we also saw when we were at sort of a low temperature, or really a normal temperature at 25 degrees, it wasn't enough to bring that back term to be larger so that we ended up with a negative delta G. So that's what that little table we went over just a second ago was sort of referring to. You know, you can in theoretical get most reactions-ish, depending on the situation, perhaps to become spontaneous, but it is sort of temperature dependent, and your values of H and S also are very dependent on that. Any questions on that there? Okay, so why don't you give this one a go for the following reaction. Delta H is minus 1204, S is 216 at 25 degrees. Are the reactants or products favored at equilibrium? So once again here, we are given the H and the S, so our equation that we just used would probably be our best choice. And again, I am going to convert my delta H into joules by multiplying by 1,000. And we also need to obviously convert our temperature there by adding 273, gives us Kelvin, and our minus 216.4 joules Kelvin mole. That is going to get us minus 1204 times 1,000, minus 298. Looks like negative here, I think. 1139512.8 joules. Feels like a lot of numbers. How about minus 1140 kilojoules here, divided by 1,000. So would the reactants or products here be favored? It should be products, yes. This means reactions should be really spontaneous, should be heading in this direction as it's written, which means we should favor our products being formed, yeah. And that is a negative, not like a almost 1140. Questions on that calculation there? Yeah. Yes, negative, which would imply that, you know, for most part, this reaction is spontaneous as it's written. So if it's spontaneous as it's written, that means it should go from reactants to products. And since it's going to products, we should see products being sort of formed. Yeah. Yeah, so if we had a positive delta G, what that would mean is it actually would be a non-spontaneous sort of reaction as it's written, and it would pretty much be staying on the reactant side or heading towards the reactant side. Yeah. Other questions? Okay. Question? Yeah, here. By doing just that math there, hopefully. Yeah. Yeah. So the result of the math above should hopefully be that. Yeah. And then I divided by 1,000 to bring it back to kilojoules at the end. Yeah. Other questions? I hope, unless I punched something wrong, but I hope that's what we got. All right, so let's talk a little bit about phase changes and Gibbs free energy. As we talked about, I think, earlier, and we talked about in previous chapter, you know, there is a certain amount of energy required to just change a substance from, say, solid to liquid or liquid to gas. And a reminder, as we talked about, that is the delta H of fusion, right, which is used to go from solid to liquid and backwards, while the delta H of vaporization is used to go from liquid to gas and gas to liquid. Remember, this is basically where we're not changing the phase of it, right, or we're not really even changing, we're not changing the temperature of it, but we are changing the phase. So this happens at the normal boiling point, right, as we go from liquid to gas and vice versa. And the normal melting point, freezing point is where we do the solid to liquid transition. So there is an entropy change that occurs at these transitions. And because it's an equilibrium process, delta G will equal 0. So we could actually look at the formation basically of steam going from liquid to gas here. And if we rearrange and solve for our delta G equation here by setting it equal to 0, we could solve for S by bringing it to the other side and dividing, in this case, by T. And that gets us down to here. This is what is known as the delta S of vaporization, since we are going from liquid to gas in this case. The delta H that we would use here would be the delta H of vaporization for water, which is about 40-ish or so kilojoules. And that's what this top number is. That is the heat of vaporization, again, specifically for water. Bottom number here is water's normal boiling point is 100 degrees Celsius plus a 273 gets you 373 Kelvin. So that is the normal boiling point there of water. And if we solve for this, we get 109 joules per Kelvin here as our delta S of vaporization. That does make sense if we think about it. We're going from liquid to gas. Is the entropy increasing or decreasing in that case? It should be increasing, right? And with entropy, a positive value shows that it is increasing, and that's what we got here. If we were sort of specifically talking about going in the opposite direction, sort of the condensation, if you will, delta S of condensation, going from gas to liquid, what would change in this equation? Just the sign, right? So it is the same number no matter which way you go. but it is exothermic, right, as you're going from gas to liquid. So that would be negative 40.79 kilojoules over our 373, going to give us a negative 109 joules per gram Kelvin. And a negative value here would imply that we're making more order, which also makes sense, right? As we go from gas back to liquid, we're creating more order, and we would expect the entropy change. You know, some people might call it entropy of condensation, is going to be a negative value. You can obviously do this for kind of the solid to liquid transition. You would just use obviously the delta H of fusion. Also, an important thing to remember is if you're not using water, right, you don't want to use the delta H of vaporization or fusion for water if it's not water. So you do need to find the right numbers for whatever substance it may be. In addition, other substances boil and freeze at different temperatures as well. So you want to make sure you get the correct temperature, heat of fusion, heat of vaporization, if you're obviously not dealing with water in that case. Also, a side note here that this equation right there may look familiar to you. We saw an equation look just like it when we calculated the delta S of the surroundings, which is actually negative delta H over T. This one here, if you're calculating the delta S of the surroundings like we did earlier, has the negative sign. That is that opposite relationship we talked about as energy goes to the surroundings. This one does not have the negative sign because it is derived from this equation. So it's very common people do this type of calculation and want to throw the negative sign in there because they remember, I seem to remember an equation that had the negative sign, and that is the one. So don't mix these two up. One, again, if you're just doing surroundings, you should have the negative sign. The other one will not have the negative sign because it is derived from this Gibbs free energy equation. Any questions on that there? Okay, so why don't you give this one a try? The enthalpy heat of vaporization for mercury is 58.5. Normal boiling point is 630. What is the entropy of vaporization there for mercury? Okay, so let's look at it. This is, again, our delta H of vaporization here. And again, as you can see, it is a different value here for mercury. In addition, our boiling point also a different value since we're not dealing obviously with water in this case. That's going to be our delta G is equal to our delta H minus T delta S, because this is once again an equilibrium process. As we talked about, this stuff happens where it plateaus, right? And both phases are basically in equilibrium with each other. In this case, liquid to gas. That means our delta G here will equal 0. Doing our rearranging, we could again solve for our delta S, which will be our delta H divided by our T. Once again, no negative on this one. We're going to put in our value here of 58.5 times 1,000. Again, just to convert it to joules, we are already given the temperature in Kelvin, which is nice. And that means that we end up with here 58.5 times 1,000 divided by 630. Going to give us something like a 92.9 joules per Kelvin as our entropy. Again, assuming we're going from liquid to gas here, that again makes sense, right? We should see a positive one. You may ask, well, how do I know I'm going that way versus the other way? I would assume in the other way they would mention something perhaps about condensation or going, from gas back to liquid. So that would tell you that in that case, as we talked about, the only thing that would change, we would throw a negative there, right? Which would then make this guy a negative, and we would end up really with the same value, just a different sign if we were heading in the opposite direction. Any questions on that there? So, as much as I hate to do it, but our good friend equilibrium, it's been a long time since we wrote K. So let us talk about our friend K and kind of bring it back into the fold here. So let's talk about free energy and equilibrium. First off, let's take a look at this first equation, which doesn't involve equilibrium. This is delta G is equal to delta G naught plus RT natural log of Q. So you may be saying there are two delta G's. What is the deal? Well, here's maybe the way you could think about it. Maybe not 100% correct in all aspects, but probably pretty close. You could think of delta G with no little knot on the top as like non-standard conditions. So what does that mean? If you remember, we sort of ran through the list of what standard conditions are. If you're dealing with pressures, everybody should be 1 atmosphere. If you're dealing with solutions, everybody should be 1 molar. Temperature should be like 25 degrees Celsius. So if you happen to come across a situation where one of those things are not true, you know, maybe you have some pressures that are not 1 atmosphere, or you got some concentrations that are not 1 molar, or maybe you decided to do it at like 95 degrees Celsius instead of 25 degrees Celsius, that would sort of be a non-standard sort of condition. That would equal our delta G under standard conditions. That is like table conditions. Like I'm going to go look it up in the table and do a little delta G is our delta G of our products minus our delta G of our reactants from the table, basically. R is our good friend, the gas constant, which once again here is actually the one that involves energy, so the 8.314 version of it. T is our temperature in Kelvin, and Q is still our reaction quotient. So hopefully you still remember how to calculate Q. It is, again, the products divided by the reactants, right? It's basically calculated, once again, the exact same way that we calculate K. So that's how you would calculate it. So again, another sort of delta G equation to calculate. And again, the way I sort of think about it is if there's something that is not under sort of standard conditions, that is your equation that you want to kind of use to calculate it. And again, delta G naught may be given to you in the problem, or again, you may have to actually just go calculate it like normal, products minus reactants, and look it up. Do you have a question? Or? It is a delta G. I know all day I've been writing 6s. They kind of look like, all right, close your eyes and they'll be like a G. Let me correct, like G. There you go. No, they are G's, or as my hand gets tired, more like a 6. That is the equation that you definitely want to use. When we do reach equilibrium, though, this equation does change a little bit. So if we're at sort of an equilibrium condition, as we talked about, delta G will equal 0. And Q would no longer be Q, but it would be the equilibrium constant K. And rearranging that equation gives us another important delta G equation, which is the delta G naught is equal to minus RT, the natural log of K. R is still the same R as above. T is still the temperature. And K here obviously is our equilibrium constant. So if you're keeping track at home, that's like 4 equations that involve G. Yeah? So as I mentioned earlier, I would highly recommend just using whichever equation sort of fits the information that you're sort of given in the problem is usually sort of your best approach for it. So with that being said, obviously, if you're given something that involves equilibrium or equilibrium constant or find the equilibrium constant, that should draw you to sort of this equation. If you're under, again, like I said, you're given maybe some pressures, some concentrations, and they're not, you know, this sort of one of everything, that would probably bring you up to this guy. And as we saw earlier, if you're given an H and an S, you should use probably the one that we used earlier. And if you're just frankly given an equation and that's it, you should probably go to a table and do products minus reactants. So, you know, you kind of want to think about it that way, as there's sort of multiple delta G sort of equations that you could use. This one, by the way, does have the negative as a result of rearranging this equation. This one is actually plus, and that also is very much missed. A lot of people always want to subtract that top one there on the back end instead of adding it, and then they sometimes don't want to do the negative on the bottom one. So just make sure you kind of keep track of those signs so you don't mess any of that stuff up. Any questions on that there? Yeah. That sounds good. I believe in you. All right. Other questions on that? All right. So let us take a look at this equation here. This delta G is equal to minus RT natural log of K. You know, really the nice thing about this is it does have K involved, which means if you pretty much still understand what K means, you can pretty much figure out the rest of this. But if you have obviously a large value of K, that should mean we should have mainly products, which means the reaction should be heading towards the product side, which means that should result in a negative delta G in that particular case. The opposite would be true if you have a small value of K. That means that we should mainly have reactants, which means the reaction is really not heading to the products. It's kind of hanging out over there on the reactant side, which would probably imply that it is going to be kind of non-spontaneous, and you would have a positive delta G. So, the K and the G sort of should work together. Obviously, if you have a K value that's 1, got almost kind of equal amounts, if you will, probably a very small value, and could have reactants or product, but pretty close to each other. So why don't we try one here? Calculate the equilibrium constant Kp for the following reaction. Here's some delta G values. I'll throw O2 in there for you. It is 0 kilojoules. Once again, like I said, I see some equilibrium action here. I'm going to go with the equation that has that in it. That seems to make sense. So we're going to use this equation here. We are obviously looking for K. R is a constant, so we do have that. Once again, that is the 8.314 version of it. Temperature here, we do need to convert to Kelvin, which would be 298 Kelvin, so we got that. We do need to calculate our delta G naught here. So again, we would go to the table and find these values, and our delta G naught would be our delta. I'm going to try to do it for you here. Delta G of our products, right? Minus the delta, it's very hard, G of our reactants there. So we're going to, in this case, take basically our products, which is 3 times 0, not too bad, minus 2 times our reactant, which is 163.4 kilojoules. That is going to give us a delta G naught there of 163, negative 326.8 kilojoules. First off, any questions so far on that? That is obviously the last piece here that we need. Once again, we have some unit situation. I got some joules there in kilojoules. So again, personally, I'm going to convert it to joules because I just like to multiply by 1,000, really. So minus 326.8 times 1,000. Once again, to convert it to joules, equals negative 8.314 times 298 natural log of K. I'm going to bring everything over here to the other side, except for the natural log part. So when I do that, we're going to divide by 8.314 and divide by 298. Also remembering that our negative and negative will now turn this like into a positive number, and that is going to equal the natural log of K when we divide everybody here over to that side. At this point, to get rid of the natural log, we need to take the E of both sides, right? So a little E action there. We don't want to insert the negative at this point since it's gone. When we do that, that's going to give us a K, and that will get us a value. We'll call it 1.9 times 10. It looks like 57, I think, is a winner there. Any questions on any part of that calculation? Let's sort of think if some of these numbers make sense. This reaction would favor reactants or products here. Delta G is negative, which means it should favor the products there, or kind of go that way. If we have a lot of products, that means we should end up with a large value of K, and I would say to the 57 would definitely qualify there as a large value of K. So again, those numbers sort of correspond to each other correctly in terms of their meaning. Any questions on any of that there? Yes, sir. Say again? It is not. You want to make sure that you use your, on most calculators, you want to find your natural log button, and above it should be the E, actually, is what you want to use on that one. Yeah. So you want to make sure. You take in the kind of the inverse of the natural log, I guess, or whatever they kind of call that E there. I call it E personally, but yeah, it's sort of like the inverse of the natural log-ish kind of thing. And when you do it, obviously, with the natural log, it just sort of cancels each other out, basically. Yeah. Other questions? Okay. And again, you also want to watch the units here. If you are obviously left the other one in kilojoules and divided by the R, you definitely will be off on your number as well, because again, you have that factor of 1,000 that you definitely will be off on. Want to try another one? Yes, sir. A question? Or yeah. I did because of sort of the information that we were given or what we were trying to find involved the equilibrium constant. So really anything in sort of thermodynamics here in our delta G sort of section that talks about equilibrium or equilibrium constant, either find it or give it to you. That's probably the equation you probably want to use, because all the other ones don't have anything to do with K, basically. Yeah. Other questions? All right. So calculate the delta G for this one. If the KSP is 1.7 times 10 to the minus 6, really an equilibrium constant. So we're looking for a delta G. So once again, we are going to go with, excuse me, we're going to go with the minus RT natural log of K here. And remember, all of our Ks are really the same no matter what the little letter is. Really, in this case, we got everything on this side. We just got to plug it in. So we are going to go with minus 8.314 joules per Kelvin per mole. Our temperature here, obviously making sure we convert it to Kelvin, so 298. And natural log of 1.7 times 10 to the minus 6. And if we do all that good stuff there, $298 and 8.314. Remembering not to forget about the extra negative there. So 32,914. These would be in joules based off of this guy, which obviously if we divide by 1,000, puts us like 32.9 kilojoules in this case. Any questions on that one? Now, again, we can also make sure everything's in agreement. I have a positive value for delta G, which means sort of reactants are favored here. And reactants are favored. I should have a small value of K, which I also do as well. So again, both of those numbers agree with each other here. Again, if you got a negative delta G here, that would mean that you should have some products and you should have a larger K value than what you started with, and you should know hopefully something went wrong somewhere. Yeah. Yes. They should be, yeah. If everything's done correctly, they really should be in agreement. If you have a small value of K, you should have really a positive value for G. And if you have a large value for K, you should have a negative value for G. And again, the reason I point that out is sometimes, we kind of forget about the negatives or miss putting the negatives in and stuff like that, or, kind of mess up on that part. So it's good to kind of think about those things and make sure, they are sort of in agreement before you box that as an answer, I suppose. Yeah. Other questions? All right, one last one here to wrap up the chapter. Delta G naught for the following reaction is 2.6 kilojoules at 25 degrees. In one experiment, the initial pressures of H2 is 4.26 atmospheres, 0.024 atmospheres for I2, and 0.23 atmospheres there for HI. Calculate the delta G for this reaction and predict which way this reaction would head. And again, here, my arrows got a little bit over. So once again here, really no mention of equilibrium constant, so I don't want to use that. I do have a delta G naught, and we are looking for a delta G, so really the only one that has both of those in there is the top equation that we saw earlier, which is our delta G is equal to our delta, I'm going to try here, delta G naught. Remember, this is plus an RT natural log of Q. in this particular case. So we are given obviously our delta G naught. We have R. We obviously have the temperature if we convert it to Kelvin, which is a 298er on that one. We do need to calculate Q here. So once again, Q is a reaction quotient, which is calculated the exact same way as we do K. So that is our products over our reactants. So that is going to be the concentration of HI. We are going to square it because of the coefficient divided by H2 and I2. And since we are dealing with pressures here, it works the same way. The pressure squared, right, of HI over our pressure of H2 and our pressure of I2. By the way, we are using this equation because when we look at the pressures, are they all standard pressure of 1 atmosphere? They are not, right? We got like a 4, a 0.0, and a 0.2. So that is, again, as I talked about earlier, sort of what is non-standard that's happening here in this equation. So we put our numbers in, and here our HI is 0.23. Again, we want to make sure we square it, divided by our H2, which is 4.26, and our 0.024 for our last guy there, and 0.23 squared, divided by 4.26, divided by 0.024 there. Looks like if I didn't mess up here, I got something like a 0.517 as my Q. Now we do have everything that we need, I hope, and we could put it in here. Delta G will equal my delta G naught, which they gave me. And as you can probably imagine at this point, I am once again going to multiply by 1,000 to convert it to joules because this guy's in joules and I don't want to screw up the units there. We're going to do our plus 8.314 joules per Kelvin per mole, our 298 Kelvin as I go down on an angle here, natural log of 0.517 there. Going through that carefully, natural log, that is not the natural log 0.512 times 298 times 8.314. And again, if we sort of get this side of it, minus 1658.56. And obviously on this side here, we get 2,600 joules. So plus a negative 1658.56 gets me something like a 941, I think, give or take a digit or two. Any questions on that there? Couple of things on this one. If this number was not given to you, once again, you would go to the table and do your delta G of your products minus your delta G of your reactants. We do have a positive value here for delta G, right? Which means we would expect perhaps reactants to be there. And kind of makes sense as well if we kind of look at our pressures. The majority of the pressure is on the reactant side, right? With our H2 pressure at 4.26. Yes, sir. Did I? I don't know if it changed too much, but let me take a look. Thank you. I think I was merging some things that way. So I don't remember what I punched in. Let me just take a look real quick. Time. So this would then become 1634-ish, I think, right? Yeah, 34.48. And gives us, what'd you say, 966? Yeah, sounds good. Thank you. Yes, sir. Not as in, yeah. 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 You would. So, for example, like we talked about, I think we did a calculation like that earlier on, but you would. So you would go, if you went there to the table, you would do your product. So you would go 2 times that delta G value for HI. And then you would then subtract it, obviously, in this case, just by the delta G value there for H2 because it's 1 basically, and you would add it to the delta G value for I2 also because it's 1, and that's how you would do it. Yeah, so always pretty much for all the values that we talked about in terms of thermodynamics, H, S, and G, if you go to those tables, you do have to multiply the values you see in there by the coefficients in the equation for all 3 of them, basically. We can do that. And for all 3 of those thermodynamic values, if pretty much all you're given is an equation, that's it, and you're asked to calculate H, S, or G, that is like go to the table and do products minus reactants is pretty much the way that you want to calculate all those guys, again, by taking those coefficients. Other questions on that? All right, so that wraps up this chapter here, which is 16, I think.